Good morning, students. So we'll move on to the next topic, that is assembly language. So from previous lecture, we discussed regarding addressing modes. We discussed about 8 different addressing modes. Okay, direct, indirect, immediate, absolute, fine, index addressing mode, auto increment, and auto decrement. Fine. So with example, you need to explain those addressing modes. Okay. So in those addressing mode, okay, we were finding some examples like move a comma b or else move r not comma some. So such kind of statements we used to face. Is it right? Okay. So those statements are the statement from the assembly language exactly. Fine. So from today's class, we will discuss what exactly assembly languages are, how they look exactly, okay, how it will be processed. Fine. So these are the few topics what we are going to discuss from today's session. Okay. So we'll go through this assembly language. Machine instructions are represented by patterns of zeros and ones. Obvious, your system or a computer is able to understand only the machine instruction pattern. Okay, that is a binary pattern. Okay, for each and every kind of operation, whatever the computer is able to perform. Okay, so the instruction which is given by the user must be converted into a binary pattern so that your system is able to understand it. Yeah. Okay, but we got some problem from this. Okay, see here, such patterns are acquired to deal with when presenting the program. Fine. What I want to express for my system, or else what kind of task I want to give for my system. Okay, if I start representing it using a binary code like series of zeros and one, okay, how it look like exactly? Just imagine, okay, for hash include studio.h. So that is what one of the program, okay, or else forget about the C program. We'll take the same example what we discussed from the previous classes and all. Okay, let me consider it as move r not comma sum. Okay, so this is what one of the example. Instead of mentioning that move space r to the base 0 comma sum, okay, if I start mentioning the binary code for that, fine, are you able to understand it? No, okay, because we cannot remember each and every binary representation over here. Okay, so to overcome that, what we need to do, we need to go for an alternate procedure. Okay, that is those binary representation, okay, should be identified by some particular name exactly. Okay, so same thing we are going to perform over here. So we use symbolic name to represent those patterns. For each and every binary pattern, whatever we are using in our whatever the system is able to understand, okay, for them we are representing or we are providing a proper particular name. Okay, so for example, just observe, we got some like examples over here: move, move, comma add, increment, branch, etc. Okay, so these are the few names or else a symbolic representation of such binary pattern what we discussed up to now. Okay, what does move stand for? A copy of source will be shifted to destination exactly, right? That is what the meaning of move exactly. Fine, but in the back end of this move, okay, when we start executing this particular instruction, okay, this move should be replaced with some particular binary representation. Remember this. The first step of execution is we need to replace this MOVE with its appropriate binary representation. Okay, same thing will be done for add, same thing is done for increment and also for the branch. Okay, so these are the what symbolic name we are calling it as. In short form, we also use to represent, okay, we are calling it as mnemonics. Okay, we call it as mnemonics. For MOVE move, we are just writing MOV. For add, we are writing complete add. Okay. For increment INC. Okay. Remember, wherever in further, okay, in further topics and all, wherever we use INC, it means what? Increment. Okay. Instead of writing complete branch, we write it as BR. Okay. Sometimes we also write like BRGT. Okay. It stands for branch greater than. Okay. Greater than. Okay. Greater than symbol what we are using, right? Okay, instead of that symbol, we can also write like BRGT. Okay, Less than will be BRLT. Okay, LT stand for less than. Okay, it's continuous. We don't have space between BR and greater than and less than over. Okay, so these are the few symbols what we discussed up to now. Okay, so next, further we'll move on. Okay, a complete set of those mnemonics. Observe it carefully. A complete set of those mnemonics and set of rules are called assembly language. Okay, if we are able to use such kind of a mnemonics with particular some rule, okay, then that language we are calling it as what? Assembly level language, or else assembly language we call it as. Yeah, okay, fine. Then the program written in an assembly language can be automatically translated into a sequence of machine instruction, that is nothing but the binary pattern, okay, by a program called assembler. Okay, by a program called as assembler. Okay, so this assembler we are calling it as a utility program of system software. Okay, so when we are discussing about the system software in 5th semester, you will be having complete knowledge about this assembler. Okay, how assembler is going to work. Okay, how it will be changing the mnemonic kind of program into a binary representation. Each and everything will be understood in 5th semester system software and compiler design subject. Okay, for time being, you just consider, yes, we have a system software called as a assembler who is responsible for converting the assembly language into machine level language. Okay, means these kind of mnemonic symbol into binary representation that will be done by assembler. Clear? Okay, fine. So here, in the next point, the assembler translates these mnemonics into a binary opcode, okay, which computer can understand. Okay, so we'll see that like how this particular example, okay, or else assembly language statement, okay, can be converted into a machine level language or machine instruction. Okay, just observe move r not comma sum we are having, right? Okay, so this should be represented in this format. Okay, so this is what we call it as. This is what we call it as machine instruction. Okay, see, move we have, right? Okay, appropriate binary representation of move, we are calling it as opcode. See, whatever the operation is specified over here, observe it carefully. Whatever the operation is specified in our assembly language instruction, okay, so that operation after converting it to a binary pattern, we are calling it as what? Opcode. We are calling it as opcode. Okay, so regarding that, we will discuss in the last topic of this module, machine encoding of machine instruction. The topic name is encoding of machine instruction. How it will be encoded, okay, we'll discuss there. Okay, just for time being, just understand. Okay, whatever the operation is mentioned over here in our assembly instruction, okay, after converting it to a binary pattern, we are calling it as what? Opcode. Okay, so this is what the operation representation over here. Okay, then later R0 we have, right? It should be replaced with its original address. Okay, that's why we are calling it as address of source exactly. Okay, then later destination is some, right? Okay, actually it is a label. Remember, this is particular label. Okay, for our for our understanding sake, for the simplicity, we are using a label called as sum over here. Okay, so this label should be replaced with its original address. That is nothing but address of destination. Okay, so this is how usually your assembler is to convert assembly level language into a machine level language. This is basic representation. I repeat, this is a basic representation. Okay, in deep, we are having many number of topics to be discussed. Okay, so that we will discuss in deep, okay, when we reach 5th semester. Okay, fine. So here, we got one more topic to be discussed under assembler. Okay, we're calling it as assembler directives. Okay, so we'll see that what exactly directives stand for. The assembly language allow the programmer to specify other information needed to translate the source program to object program. Okay, so apart from those mnemonics, your assembly level language will allow the programmer to represent other informations in your program. Okay, so that we are calling it as directives. Okay, simply, if I want to explain this directive, this is nothing but a navigation map, okay, what we are providing it for our assembler. Okay, while writing a program, okay, we are using some directives. Directives is nothing but a navigation map, we call it as. Okay, like if you are coming to one particular location, what I should perform, okay, or what exactly it means. Okay, regarding that, some information will be available in our program itself. Okay, it will make the job of assembler simple. That's it. Okay, it will help the assembler to convert the machine like assembly level language into machine level language. Remember this. Okay, we don't have any other discussion about this. Okay, we got one example. This one example. Okay, so here according to this example, just assume it. Okay, assume that programmer knows every free memory location where source program and its operands are stored in the main memory. Okay, so now in this example, we are just considering like, okay, we got one program. Okay, in previous lecture, we discussed addition of n number if n is equal to 100. Okay, so that is what we discussed, right? Using addressing mode. Okay, how we can minimize the 104 line program of adding 100 number to just 8 to like 9 lines of program. Okay, so that is what this example states. Okay, so observe it carefully. Okay, so from line number 100 to line number 132, or else 132 is blank. Okay, 128 total 1, 2, 3, 4, 5, 6, 7, 8. 8 lines of program we are having. Okay, each line consisting of how many bytes? 4 bytes. Just observe, we are starting from 100. The first line will be in 100, later 4, later 8 till 28. Total how many? Total 8 different lines we are having. And observe, 112 is the address of this particular line. Okay, so which we are labeling it as loop. So in our entire program, wherever I mention a label called as loop, that is nothing but 112. Clear? Okay. So and here we are using some operands like n, later num1, num2, num3. Okay, such kind. Then later sum. So these are the few operands, okay, which will be utilized for the execution of this particular program. Is it? Okay, see, move n comma r1. So n will be the like number, okay, total number, okay, which we want to perform the addition. Okay, so n is equal to 100. So whenever we declare these kind of variables in our program, okay, according to that, okay, we are assigning some particular memory location for these variables. Remember, okay, fine. So here we'll begin with sum. Fine. Okay, if you want, you can start with n num1. Okay, like that also. But here we are beginning with sum. So we got this variable called as sum, and later we have a num1, we have a capital N. Okay. So now we'll see how it will be stored in our memory location first. Then we'll go to the directives over there. Then sum we have, right? So whatever the result after adding, okay, we are generating, right? So that should be uploaded in the location called as a sum. What does sum stand for? Sum is a label of a memory location called as 200. Fine. So when we declare this particular variable, fine, by the name of this variable, we are labeling it for any one particular memory location. That's it. So when I declare or when I start computing this program, okay, so sum we are encountering, right? Sum means it is one variable. Okay. So sum will be mapped to 200. So whatever the value we want to store it for sum, that will be stored in this location exactly. Yeah, that will be stored in this location exactly. So wherever I represent sum, that is nothing but 200. Okay, 200 should be considered as address. Remember, it should not be considered as a value. Okay, like that you need to design your code. Okay, like that you need to use your addressing mode also. Okay, fine. Then later, apart from that, we are having num1, okay, num2, num3, like that. Total 100 we are having. Along with that, capital N also we are having. Okay, like how many number we are trying to enter regarding that. Fine. So the capital N we have, right? So capital N, we are labeling it for 204. Okay. So wherever we are targeting capital M, that represents 204 exactly. So in our example, we are considering n value is equal to 100. So inside this 204, we are storing a value called as 100 over there. Fine. So wherever I target n, we are targeting for memory location called as 204. Inside that, we are having a value called as 100. Okay. Fine. Then later, so here move hash num1 we are using, right? Okay. So 100 number we are having, and we need to enter. What are those 100 number? Is it 1 to 100? We need to manually enter. Okay. First one, 1, second 2, 3, 4, 5, 6. Okay. Like that, 300 we need to enter. Fine. So whenever I enter first number, it will be stored in this location because we are labeling it as what? Num1. Later, when I enter the second number, it will be loaded over here. Okay. In a location called as 212. Okay. Which is having a label called as num2. Why? Because here we are using this label only. Here we are not using 208, 2012 or 204 such kind. We're just using the label of this particular memory location. Fine. Okay. Now, so this is what how this program is stored in your memory. According to that, whatever the variables we are using, operands we are using, okay, where they are residing in our memory. So this is what some brief introduction, okay, or brief information we got. Okay, just assume that if I am a programmer, okay, I have each and every information regarding this memory location. Where exactly my operand is stored, where exactly my source program is stored. Okay, so loop is named for which particular memory location. Each and every information I know. Okay, just assume it. Fine. After knowing this, if I want to execute this program, okay, instead of providing only this particular program for an assembler, I would like to provide some direction for the assembler, like where exactly these operands are stored. Fine. Instead of simply providing this as a input for the assembler to execute, what I would like to do is, I want to provide some information regarding this operand store location also. Okay. You may feel like whether it is possible. Yes, it is possible. Okay. If you are using assembler directives, then it is possible. Otherwise, no. Fine. Okay. Now we'll go to the concept of assembler directive over here. Okay. This is the same example. We are not changing anything. See, starting from n comma r1, sorry, to this. So whatever the program we have, right? So that is same what I had taken the example from this topic. Yeah. Okay. Just observe move n comma r1. We are having move n comma r1. Last what we have r0 comma sum, r0 comma sum we have. So apart from this, we are mentioning something like addressing, sorry, assembler directives, sum equal to 200, origin 204, n data word 100, okay, num1 reserve 400, origin 100, okay. Then we are starting something like, we are using some different names over here, which is first, right? First we are encountering now. Okay, in our entire discussion, this is first time we are facing these kind of mnemonics or this kind of directives over here. Okay. So here we got three different columns. Just observe. Okay, the first column we are using it for naming or representing memory address label. Observe it carefully. The first column, whatever you are writing over here, okay, that is nothing but memory address labels. What are those? Loop, sum, n, num1, num2, and num_n. So these are all, we are calling it as what? Memory address labels over here. Yeah. So here we are able to write only those labels. That's it. Okay. Apart from that, we are not allowed to write anything. Okay. Then later in the center column, observe it carefully. Okay. We have operation. Okay. We have operation. Like what should be performed? Whether I should move, whether I should clear, whether I should add, whether I should decrement, whether greater than, okay, return, end, start, equals, origin, data word, reserve. So these are the what operation we are going to direct for our assembler. Fine. And later, what about this? Here, addressing or data information. So here, the address or else the data information will be available in the third column exactly. Fine. And what about this? So these are the what few assembly directives we are mentioning over here. So these are the few directions we are providing. Okay. So here also assembly directives we are using. Okay. Then later statements that generate machine instruction. So these are the what statement that generate machine instruction. Now we'll see what exactly the benefit of using or benefit of writing the same program in this format. Fine. The first line what we have, just observe. Sum equal to 200. What it mean exactly? Sum equals, EQU stand for equals, sum is equal to 200. Means sum is stored in a location or sum is labeled for a location called as a 200. So wherever we are targeting as sum or wherever we are using it as a sum, that can be replaced by a number called as 200. Okay, and this 200 will be considered as an address. Remember, okay, where we are using the sum, here we are using it as sum. Okay, so this should be considered as address. What is the original value of this sum? 200 exactly. Okay, instead of finding where exactly sum is located in this memory, okay, what we are doing, we are providing information for the assembler that if you find sum, just consider it as a 200. See how simple we are making the task for assembler. Okay, no need to search. If a programmer know about the information regarding where exactly program is stored, where operands are stored, he can provide some information for the assembler also. Fine. Based on that assembler, it will start execution. Okay, and the time taken for the execution will be less. Obvious. See, every time your assembler should start search for whenever it find a location, whenever it find a operand called as sum, it should find where exactly it is stored. Yes, it will find like it is a label for a one particular memory location. What is that memory location? 200. Every time it need to search. Instead of that, in my program, if I'm using 100 times a operand called as a sum, okay, then 100 times your assembler should find the location of the sum over there, right? So instead of that, only once I am representing, sum will be equal to 200. So wherever I find word called as a sum, it will be considered as a 200. That's it. Fine. Okay. Now, once I'm done with sum is equal to 200, where you are exactly pointing for this location. See, we are pointing for this location. Okay. Then later, where I should point next, I would like to provide information regarding this n also. Okay. I would like to provide information regarding this n also because it is also a label, right? It is also a label and it is also a operand. Okay. Regarding this also, I would like to provide information for the assembler. Okay, fine. So next, we are using a keyword, observe it carefully, origin we are using. Origin means what? You are in 200. So shift your pointer, which is pointing for 200 to 204. So origin 204. Okay. So now you are pointing for 204, that is nothing but n. So now we'll describe what exactly n stand for. Observe it. N, we are using a n as what? Data word. Remember, n will be utilized as data word. So you may ask why we are not naming that sum as a data word over here. Okay. So sum will be computed and result will be stored inside the sum later. Okay. But here, inside the n, we are having some information that should be utilized for the computation of this complete program. That's why we are naming n as data word. Okay, n will be considered as data word. So wherever we are using a capital N, what is the like value for that particular capital N? Okay, what it is here 100. Fine. So inside that value, what we are having is 100 exactly. Fine. So 100 should be considered as a data word. Okay, what is the value of that? Like what is the representation of that 100? N exactly. Fine. Okay. Then later, after this, we need to come for num1, num2 till num(n) exactly. Okay. Num1 we have. So we'll go to the next. Num1. Fine. Num1, reserve 400 we are writing. Why we are writing it as reserve 400? Here, num1, reserve 400. See, the difference between these two. Okay. The difference between these two, starting from 204, 208, okay, to till 604. Okay. So from here to here, we are reserving total how many bytes? 400 bytes. Why? For reserving or for storing one number, 4 bytes we need. Like that, if I want to store 100 number, then how many bytes we need? Total 400 exactly. So total 400 bytes will be reserved from num1. Okay. So here the complete operands are uploaded. Okay, when user start typing the first number, second number, third number till 100 number, so whenever he enter, okay, that will be uploaded in this particular location. So we are reserving this 208 to 604. That's why we are writing it as num1 reserve 400. Then later, so we are done with expressing, or we are done with explaining what exactly these labels are. Okay, for our assembler. Then what I need to do, what I left with, I need to start the execution, right? Then origin. See, from 604, I need to come back to 100 exactly, because this is what the first line of my program, from where I need to begin the execution, right? So we are writing it as origin 100, fine. Then we are using a directive called as a start. We are using a directive called as what? Start exactly. See here, start. It indicates from here, we are beginning with the original program. Okay. Start to return. Okay, remember, start to return whatever the content we are having. We are calling it as statement that generate machine instruction. Remember. Okay, so before this, whatever we are having, before this start, whatever we are having, That is the explanation regarding the labels, whatever using in your program. Remember this. Fine. Before start, whatever we have, that is the explanation regarding the label. Okay. And between the start and return, whatever we have, that is the statement which is generating the instruction, like machine instruction. Okay. Then you may ask, after return, what we may be having? Will be having end. End of what? Start. So what you are starting in this location, that should be ended over there. That's why we are writing it as end start. Yeah. So these are the few directives we are providing for the assembler. See, these are the directives: return, end, start, origin, reserve, data word, okay, origin equals, okay. So these are the few directives we are providing it for assembler so that it can easily start converting the assembly level language into machine level language. Fine. I hope you don't have doubt regarding this topic. Fine. Okay. Next, we'll see what exactly the execution part of assembly language will be. Okay. So, okay, fine. We are writing the program using assembly level language. Okay, fine. So how it will be executed? Fine. That is what the concept we want to discuss now. Fine. Assembly and execution of program. Okay. So we are listing like directives. Second, replace all mnemonics with binary representation. Replace the operand name with proper address. Branching offset, which is the distance to the target. Then symbol table, pass to assembler. Okay. Problem of forward branching. Then finally debugging. So these are the few procedure we need to go through when we start executing any assembly level language. Okay. So the first one we have is directives. So when we start the execution, so whatever the directives we are mentioned in program, okay, so that should be analyzed. Okay. So because in further, okay, if you are encountering such kind of a word, it should be replaced with proper address. Okay. So few address will be specified or few guidelines will be specified in your directive part. Okay. So that should be analyzed first. Okay, so this is the first step of executing assembly level language. Okay, second, replace all mnemonics with binary representation. So those like mnemonic kind of words like add, subtract, multiply, divide, move, load, store, increment, decrement, or else a branch. So these are the few mnemonics we are using, right? So that should be replaced with its proper uh, like opcode or else the pattern, binary pattern, whatever we are calling that, like it should be replaced by binary pattern. This is what the second procedure. Then later the third one will be replace the operand name with proper address. Yes, the source and destination, whatever you are mentioned in the instruction. Okay, so that should be replaced with proper address because there also we are using some kind of a labels over there, right? Okay, fine. Then later branch offset. Okay, what does this branch offset stand for? See, in previous example, if I want, sorry. Okay, so here branch where it is located 124, right? Branch greater than 0 loop. You are in location 124, but branch is saying like you need to go for a location called as a loop. Then what is the difference between these two? 12 is the difference, right? 1, 2, 3. Okay, means three different words we need to go backwards. So this difference we are calling it as offset. Remember this. Okay, so if you want to execute this program, okay, we need to discuss about the directives. Later, replace all these mnemonics with binary representation. Replace the source and destination symbols with their appropriate address. And later, if you have branch statements like this, so the difference what we are having. So in this example, observe it carefully. Reverse branch it is. You are in 124 and you are targeting for 112. In some cases, it will be forward branch. It will be forward branch. We will discuss that. Okay, it will be forward branch. Okay. So what is the difference? Whether it is forward branch or reverse branch does not matter actually. Okay, like how many places you need to take a deflection. Okay, so that is what the matter. Okay, that number we are calling it as offset. Remember. Okay, that number we are calling it as offset. So that should be identified. Yeah. Then later we got very important thing called as a symbol table. Okay, so just let me consider it as a symbol table. Okay, it will be having two columns. For time being, you need to consider it as a symbol table. Okay, because internally we have a lot of discussion. You will get to know about this when we are discussing about the ATC, then later system software topics and all. Okay, there you will be having better knowledge about this. So symbol table. Okay, so here we'll be having symbols, appropriate address. Okay. Whatever we are using or whatever we are encountering while reading the program, okay, just observe, like if you are having a instruction like add, okay, r not comma sum. Consider like this is what the first line of your program, okay, and so this is what the first line, and this is what the fourth line. In the fourth line, we are having something called as subtract r not comma sum. Okay, if you are having these two instructions, okay, so this is what the second line and third line. Fine. When I come to this first line, okay, see what I have, add we are having, right? So appropriate like binary pattern will be replaced, okay, for this particular mnemonic. Then when it comes for the source, what it is, R naught exactly. What is that symbol? R naught. Okay. Where exactly residing? That will be searched by your assembler. Okay, it will be searched for memory or it will be searched for the processor. Okay, finally it will come back with some address. Example like 456. Consider the address of this R naught is 456. So it is found when I try to execute the first line, right? Okay, so this is what the information I got. Like in 456 location, R naught is 4. So this address will be maintained inside 456, this symbol table. Symbol, appropriate address. Okay, then later, sum we have. Sum is at location called as a 200 according to previous example. So sum will be uploaded over here. Okay, 200. Now you may ask why we need to represent or why we need to manage this kind of information inside a symbol table. Okay, observe it carefully. In line number 4, we got R0 and the sum, right? So we found that R0 is at 456, sum is at 200 location. Okay, for finding this, consider like 2 seconds I took. Okay, for finding these two information, where exactly they are residing, I took 2 seconds. Okay, so after executing second and third, again we got in fourth line R0 and sum. Again, I need to spend 2 seconds for finding where exactly they are residing in our main memory or inside the processor, right? Okay. So instead of that, what we can do whenever I get these kind of symbols or these kind of source and operand, I need to first search inside the symbol table. Okay. If the entries for R0 and sum is already available in the symbol table, directly we are fetching 456 for R0 and 200 for sum exactly. If they are not residing in symbol table, you need to go for searching. Yeah, so this is what the advantage of using symbol table over here. Okay, so we need to update the symbol table along with this conversion. Okay, so whenever we find the source and destination operand, okay, so appropriate address, wherever they are residing, okay, so that should be updated in our symbol table, so that in the next cycle or in the next line, if you are facing the same source and same operand, or else different operand and different source it may be, does not matter, but same R naught or sum if you are facing, okay, then you can directly come for symbol table and you can get the information. Otherwise, you need to upload. Okay, whenever we find those kind of symbol, we are just updating our symbol table. Okay, for future use. That's it. Then later, we are having 2 pass. See, whatever we are performing, right? Okay, in symbol table updation, that we are calling it a 1 pass. That we are calling it as 1 pass. Then what exactly 2 pass assembler stand for? Okay, what is this 2 pass assembler? Okay, problem of forward branching. See, 2 pass assembler means we are scanning our entire program twice. Okay, in first line we had add R0 comma sum. In second line something will be there. So we will start from the first line and we will be scanning each and every line. Okay, to get the operands. Okay, with appropriate address. Okay. Meanwhile, we will be updating our symbol table. So if you do it for once, we call it as single pass or 1 pass. Okay. Twice, if you are performing, we are calling it as 2 pass. Okay. You may ask why we need to perform twice over here. Okay, because we are having this problem. Okay, the branch we have, right? Branch greater than 0, then loop we have, right? Where exactly loop it was? In my previous slide, 112. Okay, where branch was there? 128, right? So reverse it is. Okay, so here we are labeling it as loop for location 112. Fine, but in line number 112, we don't have an instruction consisting of a word called as loop. Okay, so no need to worry about that. But while reading this particular 112, okay, we got to know like loop is a label for 112. So this will be also updated in our symbol table already. Okay, we'll be having the entry in our symbol table, like loop means what it is, 112 exactly. Okay, because before this we had not found loop over here. Here itself we are finding. Okay, fine, let it be in our symbol table. Then when you come to location 128, yes, you are facing something called as a loop. Directly we are referring for the symbol table as you got to know like 112. Means if it is a branch greater than 0, go to location called as 112. We don't have any problem in case of a reverse branching. But okay, just observe, you are having branch greater than 0 loop. Okay, observe this example, very very important. 128 location in 128, then 32, 136. In 136 location, if I am labeling it as loop. Okay, so this is how, like, same. Okay, instead of going backward, we are coming forward. Okay, so now loop means what? 136 exactly. See, while processing line number 128, we are facing like branch greater than 0, right? We are facing branch greater than 0. In front of that, what we have? Loop we are having. What is loop? We don't know, because before 128 we never found loop means what. Okay, where exactly loop means. Okay, we didn't found word called as a loop over here. Okay, so now what we do during the first pass, okay, while scanning first time symbol table, okay, this is what the symbol, this is what the address. Okay, so now after processing 128, we found something called as a loop, right? Address we left blank. Remember this, we left address as blank because we don't have any information. Okay, but okay, fine, leave it, forget about this. Okay, then we will be executing like 132. Fine. When you come to location called as 136, yes, you found that, yes, it is a label, right? It is a label. Now you are uploading it for loop as 136. When second time, okay, during the first scan, you'll be not having information like loop means 136, but during the second scan, okay, after scanning complete, okay, you'll be now having information that loop means 136. Okay, so now, wait a second. So in the first pass, I left loop means what? Loop means what? Blank. Okay, this was at line number 128. When processing 136, we got to know like loop means 136 exactly. Okay, now this will be blank itself during first pass. Once I'm done with scanning entire program, okay, when I come to the second time for scanning, okay, I found that yes, this place is vacant over here. What is that loop exactly? And now I have a information that from first pass, I found that loop is equal to 136. So 136 will be uploaded over here. Okay, so this is what the problem what we are having. If you are only depending on single pass, if you are depending on single pass, this place will be empty. Okay, so during second pass, this will be overrated as 136. Now we don't have any problem. Okay, so this will be done by your assembler, single pass and double pass. Okay, fine. After this, all conversion, we need to go for debugging the program. Okay, for finding whether any error is available or not. First, get the directives, replace the mnemonic, replace the operand with proper address, get the branch offset, go for updating the symbol table using one pass and two pass. Okay, later go for the debugging. If you find any error, intimate the user, you will just change the syntax. Okay, then finally it will be executed. This is how your assembler executes the assembly level language. In the last, the number notation, like how we are representing the decimal, binary, and hexa numbers. Okay, according to your assembly level language. If it is binary number, only sharp sign is enough. See a 93. Add a 93 comma R1 with a sharp sign. Means 93 should be added to content of R1 exactly. Okay. In case of decimal number, we are representing using only sharp sign. But if it is a binary, along with sharp sign, we need to use percentage sign. Okay. So this is what the representation of 93 according to binary exactly. Okay. So hash percentage 1011101. If you are not mentioning percentage over here, it will be considered as like 1011101 will be added to R1 exactly. It will be considered as a decimal number. 1011101 will be considered as a decimal number. You will be getting wrong result. If you want to make this as binary itself, then you need to use a prefix called as, along with sharp. Sharp is must exactly because we are representing the number. Percentage sign you need to use. And later hexa number we have. What does this hexa number? Okay. like 5D. 93 can be represented by 5D exactly. Fine. So 5D if you are using, then the prior to that, what is the prefix we need to use? Dollar sign. Okay. So only sharp for decimal, sharp with percentage for binary, then sharp with dollar sign for hexanumer. Okay, fine. Okay, students. So this is it for now. So in next class, we'll discuss about like basic input output operation. Okay. Thank you.